The thymus gland shrinks as we age. So the cells that get exposed to the hormone from the thymus gland, yeah, they'll stay with us for life, for the most part, because of the thymus gland shrinking. It's formed cells. Now they just have to wait for whatever they are created to fight. Vaccinations, for example, we get vaccinated for like polio. What does that do? It stimulates the T cells that will fight the polio virus. And they just sit and wait. And if you get exposed, they take care of it and you don't get polio. Yeah. The platelets. Now remember, platelets are not a full cell. They are a fragment. They're very important though. Platelets, they play a role in hemostasis, meaning heme, red, bleeding. Hemostasis, whenever the body is bleeding, well, the body itself wants to stop it. So hemostasis is the cessation, the stopping of bleeding. It's not hemorrhaging, okay? Hemorrhaging, the bleeding that happens with hemorrhaging is a totally different type of bleeding. The body does try to affect a hemorrhage that's occurring. The problem is it's too much blood loss occurring quickly, and the cells that function to stop bleeding are going to go into positive feedback, and it's going to actually end up killing you. So if the hemorrhaging doesn't stop, okay, if we don't stop the hemorrhaging, it's going to be, the body's not going to be able to do that. But normal circumstances,
we were talking about positive and negative feedback. If our temperature goes up over 102, would that be positive?
now, the body's going to be doing negative feedback to try to control it, but the problem with getting the temperatures at like 103, 104, the biggest issue with that is we're breaking down proteins. That becomes what's detrimental. So negative feedback is trying to stop it, but based on it not stopping, the biggest part of the body that gets affected is the proteins. And that, if it gets to a certain point of proteins being affected, the body can't replace them. And that's when death comes about. Under normal circumstances for bleeding, and I know you're probably thinking, well, Dr. Burnett, that don't sound like a normal circumstance, okay? But I don't know, let's say, give you a good example. Now, this was a long time ago, and why I did this, I have no clue. I decided that I was going to cut an onion like this.
Oh, God.
With the knife, holding the onion.
Oh, God.
Go figure, right? I was only like 19, okay? Well, yeah, what did I do? Went straight down through my hand.
Wow.
I couldn't stop it, so, you know, I'm not bleeding to death. You know what, I'm bleeding, okay? So, get to the hospital, they sew me up, send me home, bleeding eventually stops. Well, that's cessation of it, okay? So, it needed a little bit of help, the stitches. The stitches were able to take the two sides of the wound and hold them together. And in doing that, it allowed materials that were in the blood to do their job. You know, look back on it now, I probably could just use them little butterfly things, but hey, I didn't have any. So anyway, okay, so my platelets, They're important when it comes to bleeding. They are a small fragment. They are from a cell called a megakaryocyte. Mega means large. Karyo means nucleus. Cyte means cell. It's from a large nucleused cell. And it's just, do you guys remember in the structure of bone, the bone marrow is in all of that spongy bone, that trabeculae type stuff? So this cell pretty much is stuck in some of that trabeculae, and as the blood flows by it in the marrow cavity of the bone, as blood flows by, little pieces just get broken off. So they're just broken and broken and broken and broken and broken. Okay, so it ends up being these little plasma membrane pieces. Okay, and whatever material made it into them. So we've got these little platelets that will begin to travel around in the blood. They do have a complex internal structure. They don't have a nucleus or anything because they're just pieces, but they do have mitochondria. They have canalicular systems, which means these little circles of material, okay? We end up with granules. They have their little pseudopods because that helps them to move, okay? They're going to have lysosomes. They're mitochondria because they got to have energy. They got little microtubules, microfilaments, granules. All of that is existing in this little platelet. Now, when it comes time for those platelets to function, for example, at the time of a cut, okay, one of the things they can do, they can secrete vasoconstrictors. Constrict the blood vessel. All right? That blood, because see, when we begin, remember how we talked about we've got the really large vessels, but it's actually at that capillary level everything occurs. When we do something like that cut or paper cut or something like that, what we have actually breached are our little capillaries. Yeah, you might hit a larger vessel depending on how deep the cut may have gone, okay? And of course, when the cut's really deep or severing something or something like that, you know, then it's, you know, lots of blood and bigger vessels and all that sort of stuff. But under these conditions we're talking about here, okay, we break a vessel. Well, when we break a blood vessel, we need that vessel to begin to close up. We don't need that vessel to stay open and all that blood freely flowing. But here's the thing. Throughout the day, 24/7, blood vessels, whether we know it or not, are constantly breaking and repairing. It's just the way our body is. So this is pretty much a process that's occurring all the time. But yes, when we breach the inside to the outside of the body, we need the vessels to begin to constrict. We need to form what's called a platelet plug, meaning the two ends that got cut, okay, the area needs to begin to form a plug so the blood's not continuing to flow. They can secrete procoagulants. When something is coagulating, it's clotting. So they secrete procoagulants, the ones that come before clotting factors, okay? And they will be helping with our clotting factors. People who are deficient and clotting factors, something as simple as a paper cut, something as simple as like that cut that I made, you know, through my finger, could actually kill them. So depending on the clotting factors and so forth, bleeding disorders can be very disruptive to people's lives. We need to make sure that once we have a clot, the blood stops, that we are able to dissolve that clot. And we need that clot to dissolve completely. We don't need any pieces or parts of it left behind. We need to make sure at the time of the breach that we attract the leukocytes, because the leukocytes are going to help us with any of those foreign particles trying to invade, like the bacteria that we have on our skin, okay? Bacteria that's out here around us, all right? So platelets secrete chemicals that attract these cells. And when that chemical is going through the blood, these white cells, these leukocytes, they will actually rush to the area that's been breached. They need to be able to internalize and destroy that bacteria. Otherwise, things don't end up very pretty, okay? You can get infected and the pus and all this other type of stuff that might try to come up. Then, once we have sealed, stopped the blood flow, taken care of anything that tried to invade, we now need to focus on healing. So let's get some growth factors going. Let's stimulate mitosis so that we can form the cells to repair those vessels and any of the tissues around them. Give me the fibers I need, so the fibroblast that we find in the plasma of the blood can come to the area, and we can give rise to fibers that will help us form that clot, that web that will create the clot, help create smooth muscle cells so that I can repair my blood. Do you see where I'm going with this? Okay? So, in production of the platelets, it's called thrombopoiesis. The way that it gets promoted is actually from the liver. The liver will actually say, give us more platelets in the blood. Platelets have a lifespan of about 5 to 6 days. They're really cool in all aspects. Take a break, be back at 10:30.